Hello all, welcome back. Hope all of you are keeping fine and safe. So this is an extra lecture actually. Thought of introducing you to some of the concepts in the interrupts particularly and GPIOs just to revisit and how to code it. And if you have the board with you, you can definitely try it. Otherwise, I just want to get you motivated rather than the continuous theory lectures. So I have the board with me, and you can see over here it just connected. And unfortunately, you not got familiarized with the board. We didn't have that much opportunity. But let's get started. So here is a board. I just connected it to the USB, and it's up and running. So I can show you some of the interrupt examples which I was not able to show you during the lectures. So in this particular example, I'm trying to actually show you the hard fold interrupt. If you forget, please go back to the lectures and refresh yourself. So hard fold interrupt is something which gets triggered if you try to access a wrong or reserved memory region, for example, or something like division by zero happens. So it is a system interrupt. So you cannot actually edit it. It is there by default. It is not a configurable interrupt, or it doesn't go through the NVIC that we talked about. So I'll show you that. So here in this example, what I'm actually trying to do is try to access a certain location, this particular location. And this, if you go back and see the memory map, it is a reserved location. So if you try to write to this location, it will trigger a hard fold. And then what we do is we write something in the handler corresponding. So this is the interrupt service routine corresponding to the hard fold handler. So we write something here so that it turns the red LED on and off with certain delay. So that's the thing I'm going to do. So there are certain things that we need to do. First of all, of course, you did not need to actually configure the interrupt here, because hard fold interrupt is there by default, and unless you mask it, it will be always there. So no need of configuring the interrupt like we did in the class. So that you can be a safer side. But the objective is actually, so of course you have to write whatever you want inside the interrupt service routine here, inside the hard fold handler, right? As usual, proc and NP are the things that you have to be careful about. And then of course you use this export hard fold handler, so it is available to the processor at any stage. It is something like making it visible to the processor. Okay, so whenever the hard fold happens, it goes to the hard fold handler, and it is going to execute whatever is there inside here. So there are certain things that we do, something like this is coming from a main function. Even though the system itself, the core itself, during the interrupt handling process will put the things into the stack, something like register R0 and the link register, the program counter, and some other registers like R12 to R15. I think they put into stack pointer for the safety. But inside this module, I'm going to branch to certain functions, read on, read off, then delay, and also for the safety of all the parameters that I already have, and also to return to the correct point in the main function. I'm actually storing the whatever value is there in the stack pointer and pushing the link register value to the stack. And then I'm popping at the end of whatever I want to do. At the end of it, I'm popping the last content of stack, which is nothing but the link register, to the program counter, so that it goes back and execute the corresponding program in the main, right? So that's the objective. So inside here, what I'm actually doing is I'm actually making on the red LED inside the board, then giving some delay, of course, and then make the red LED off. That's what actually I'm doing it. So red LED on, then delay, red LED off, then again delay, then it goes back to the main program. And then how to configure the red LED. So that's the critical aspect. So you have to go back and see the manual. So I'm just showing you here the manual. So this is a built-in LED that I'm showing you here. So we have a built-in LED here. So this LED is our friend, and it is actually an RGB LED, which is as shown here. The red LED is connected to port B's 18th pin, and the green LED is connected to port B's 19th pin, and blue LED is connected to port D's first pin. So that is the hardwiring part, which is already done for you. But the important part is like, as we discussed during the GPIO session, you have to actually do certain things, right, to enable these GPIO ports. I just want to recollect that the first step is, of course, to enable the clocks to GPIO B and GPIO D in this case. That's very important. Second aspect is these port B and port D, these are multiplexed. So you have to enable them as GPIO. So individually port B 18, 19 and port D 1, you have to go and enable them as GPIOs. Basically enable the multiplexer so that it acts as a GPIO pin. Then individually, if you see port B 18, 19 and D1, you have to actually configure them as outputs, correct? And then of course, this is actually something like the negative logic, right? So if 0 value comes here, that means this is already connected to plus 3.3 volt, and then it gets connected to the ground if 0 comes here, and then current flows through this LED and it glows up. So if you write 0 to this pin, this glows up. If you write 1 to this pin, it switches off. So that is very important. It's negative logic. Please remember that. Okay. Now let's do this. That's what exactly I'm doing here. So at the top, I'm just labeling the respective locations. For example, this is a clock. Just made the things here. So inside this is the clock. So I'm just, this address is mapped here, labeled here. Similarly, I'm mapping port B's 18th, 19th pin, port D's first pin, corresponding location here. You can always go back and see the manual. Please don't by heart here. And this is just to make life easier for you. Okay, so that's important. So that you can just need to call these labels inside the code. Otherwise, calling this becomes very difficult and not very readable for a user, right? So that's done. Then GPIO's port B's set output register, clear output register, toggle direction register, and similarly D's respective registers. And actually, you don't need a toggle register because I'm not using it, but I just called it. Okay. And then the blue mask, red mask, and green mask. That is very important, right? If I go back here, blue is basically D1, right? So first pin. So that's the critical part. So port D has 32 pins. Please remember that. The first pin is what I'm caring about. So that means when I say the blue mask, once again, if you're losing it, let's concentrate on blue mask. It is connected to port D's first pin. So that means let's see what is blue mask corresponding to. So this is the value. All are zeros except the last one, which is actually 0, 0. Remember, this is hexadecimal. So 2 stands for 0, 0, 1, 0. So remember, it is port D's first pin. So 0th pin is 0. First pin is that we are worried about. So that you have to put as 1. And then other pins are, you don't have to worry about, all are 0, 0. And that is why it comes 2 here, because 0, 0, 1, 0. Okay, so that is the important aspect. So 0, 0, 2, 0, 0, 0, 1, 0 maps to 2 here. So similarly, if you see port B is 18 and 19, okay, and sorry, the red mask is port B's 18th pin. So let's see the red mask. So port B's 18th pin, remember that, okay. So 18 actually, only 18 I have to put 1. All others, 18th bit I have to put 1. All others are 0. So this one, for example, corresponds to bits 31, 30, 29 and 28. This one corresponds to 27, 26, 25, 24. This one corresponds to 23, 22, 21, 20. And this corresponds to 19, 18, 17 and 16. Okay. And out of that, 18 is what I have to put as 1. So that means 0, 1, 0, 0, which is nothing but 4. Similarly, 19 is 1, 0, 0, 0. So that is why it is 8. All other pins I don't have to worry. So that is how you put blue mask, red mask and green mask. And again, you can do it, this hard coding inside the code, but this is just to make easier for you. So if you want to enable blue, I just need to use this. Red, I just need to use this. And green, I just need to use this. And similarly, I'm giving a delay value here, which is some high value, just for our understanding. Okay? And then this, I already mentioned, this is a location where which is forbidden for us. If I write something to this location, it will trigger a hard fault. So now let's go inside the main code. So this is a main code as usual. So main is somewhere between this to this, correct? So here what first step it does is it goes and initialize the GPIO, and then it loads some value, doesn't matter what value, and then load the address location, the forbidden location, and then write this value to that location. The moment you do that, it triggers an interrupt and it goes back all the way to your hard fault handler. And now let's run this so that it becomes very clear to you. So no error, fortunately. And here, certain things you have to do. You have to go and set the things. So please follow the manual. So I've done already for you just to show you. No more using the simulator. I'm using something like PE micro debugger where actually the board is already there. Okay. So that's it. Press OK. And now you just go back to debug, usual stuff. And it will open up a new window, which is something new for you. You can see that I already connected the board here, and that is auto detected. And you have to select this board, our board. Okay, KL25Z128 is our memory size, and that's it. You connect. So this window will pop up, evaluation mode, and then just you go ahead. Again, it will ask one more time. You just connect, and then that's it. It's done. And then, as usual, it just goes and executes from wherever we used to follow. Right? Similar, nothing, no change. So we'll just proceed this part, which is very clear to you by now. So I'll just go here, and it reaches the main. Now let's branch to the GPIO. So the first part is to enable the clock. This is well known to you, so I'll just skip it. In between, you can see over here. So just keep an eye on this. So F11, 11. So just the moment I execute this, port B and port D are enabled, and that's what this is for. We just need to enable the respective bits, and this part we discussed already, so I need not spend much time here. So that means this is enabled. Now let's continue. So this is now in port B's 18th pin. So here I will just take the 18th pin for you. So what objective here is this multiplexing, which is here, is disabled now. So by doing this, I'm going to enable that. So you see here, this is already enabled. And similarly, let me go back to port 19. So here it is. So this is also enabled. Then we will go to port D also. So let's go to port D, and port D is already enabled here. So that's the things. Those three are completed. Now the objective is to set the DDR register, direction register. All of them are output. So correspondingly, I will set that. And then here I'm actually setting out the. So basically here, what the next few steps I'm going to do is I'm going to set the port B's both output registers disable any color. That means both will be set as, so here both the all three actually, all three are set as high, so that at the start, at the initialization part, the LED is not glowing. So you can see here when I start, unfortunately the red LED is going. So what I will do is I'll just minimize the screen so that you can see it. Sorry. Let me just try. Okay, it's not working. That doesn't matter. So here, for example, now I'll just quickly show you. After that, the LED, everything is off. Similarly, the D part, which is again I'll show you when I do this. when I do this part, the blue one, which is the D port. Now that's the end of the initialization part. So I'm back. So at the initial init GPIO, what I did actually is I enabled the clock to port B and port D. I made the pin multiplexing for these pins as GPIO. Basically, port B is 18th, 19th pins, and port D is made the GPIOs enabled, the multiplexing part. Once I did that, I individually went and made the direction register as output register in 3 of them. And at the same time, I enabled the set output register in 3 of them so that a high value is set in all these 3 pins, which will make the LED absolutely 0, right? Nothing is there. You can see over here, nothing there. And now we are almost there. So I'm in the main. So initial part is done. Now I'm going to access that non-accessible location, forbidden location. So I go here, I load the address. Now I'm going to write this value to this. Immediately it went to the hard fault handler. So if you don't have the board, it will never work. So that's the important aspect. Okay. So if you have the board only, this will work. Now I'm here. So as I said, I'm pushing something to stack just to ensure that when I return at the last stage, I can return back to the main program from where I came, right? So in this case, I'm going to, so now just check here. This is already blank, okay? Now if I make this LED on, which is actually the entire function, which is here. So corresponding register, I'm going to clear it, okay? Earlier we were setting it PSOR, now PCOR. So if I do it, the moment still it is off. The moment I do this, you can see the LED is on. So I turned on the LED. Now it will go to a delay operation. Then it will turn the LED off. So what I do is I'll put a breakpoint somewhere in pop PC. I run it and keep you with this so that you can actually see it. Yes, off. We are back here. Okay. The moment I press F11, it goes back and keeps this location, not this location. So it again loops one more time inside here. Okay, so that is the debug mode. Now I'm going to come out of debug mode. Okay. What I actually do now is I already compiled it one more time. Let me just make sure I compiled it, no errors. There is an option to load whatever you do. So debug is just to check everything is correct or not, right? You don't want that irritating window to come up when you do it in actual execution mode. So when you want to directly program, so the bin file is already created when we do the compilation. The bin file is created. That bin file can be downloaded to the board using this load icon here. So I press load. This window opens up. We just connect it. So you can see everything is done. So load programming successful. And you will see that there's nothing happening. In many cases, there's a reset button right here. If I press that, this will work. But for some reason, some of the boards have some hanging issues. So you have to switch on and switch off the power. So for that reason, I need to plug out the USB. So I'm going to plug out the USB now. Okay. And then plug in back so that you will see the things blinking. So for that, so you see it is blinking. So what essentially happens is it is going to the hard fault again and again. And inside the hard fault, I've written a code to blink the LED. And that is the beauty about it, right? So hardware is saying you just change the software, you're going to get this beautiful, right? And now, okay, so let this be running. Okay, I just want to close. Now I'm going to make certain things very simple for you. Okay, so far you just see this code, so many lines of code for just simply doing some very, very trivial things, right? And this is going to be very, very tedious if I'm going to write the assembly language for a longer program. And that is where the C helps. But as I said, nothing is more optimal as an assembly language. Okay, it's very, very important to notice that. And that is why we introduce assembly language to you so that you are familiar with it. It should not be alien to you. But now onwards, we will stick to the C because that is much, much easier. And a lot of things we can do with a single line of command instead of so many lines of command. Okay, so before introducing C, there are different types. One is actually to directly use in something like Keel or something like GCC environment. That is one way to go about it. And the other way is actually something which is an open source online cloud-based compiler, which I have a separate session on, which is known as mbed. Okay, so we'll go to that. That is much easier. But then the problem is, if I start with that, you'll be really lazy. It is something even more simpler than the processing software that you use in Arduino. Okay, so life is very easy. I made it a mess for you so that you understand it in a very clear, thorough way. Okay, so what is happening below, whatever code that you like. So now I'm going to close all these, or maybe I'll keep this for a moment. I'll just add one more source file, which is already written, and which is C. The same code, the C part. Okay, so let me just open up the interrupt. So it's right here. So this is exact equivalent. So I'll just close these things so that these two are exactly equivalent. Okay. Only difference is this is in C. And see how much difference is. This is so much of line of code, and this is only this much. And it's very easy actually. So let's do. I'm including a library which is MKL25Z4H, which is our thing. And if you go and see here, it is right here. Okay, so you can see many things are already declared for you. So you can see like the interrupts priority. So these are the non-core interrupts. This is what I was talking about. And then everything is inside here. So let me just ADC, for example, all the registers, and then details of ADC, etc. Everything is detailed here. And let's go here and explain. So then time, I'm not using it. So and then this is something like the export. Okay. Whatever you are declaring below, you have to declare at this point. And you can actually copy everything and then put as an interrupt c.h and then put all these files there and then include that here. That is what typically people do, the header files, right? So these are headers. You can actually create a separate header file and put all these in there. That's now going further. So here actually is the main function similar to our this main function. Okay, very similar. So this is int main. You have to be careful about that, and nothing goes in void. And then as we do here, Gpio init Gpio branch, I'm going to do the initialization of Gpio, and then I'm going to write something to a non-accessible location, same location as in previous. That's these two commands too. Okay, and this is a low-level way of writing it. Okay, int volatile const, so a p register, I'm going to store this value. And then this P register, I'm going to actually, P register is pointing to this location. And I'm going to write the same value which was tried out in the previous case to this register, and it will create a hardware interrupt. And it will go to this handler. And you see, here the handler had so many lines of code. Here it's just 3 lines of code, and very easy to interpret also. Read on, delay, read off. Read on is somewhere here. And you see, it's very simple. So let's start from the GPIO LED unit or GPIO unit. You can rename whatever way. So it goes here. First step is enabling the clock. So sim is the register. In that SCG5 is the location I'm interested in. I just want to write this. So I just want to make sure it's so easy. Let me write sim here. Okay, so you can see the list here. If I put this button, all the options will come. All the registers will come. That's the beauty about it. And then you select the corresponding thing. Let me delete it. And this operation is the OR equal to operation. That's what we were doing it. We were doing this OR operation so that we don't disturb the existing values. That's very important, right? So if you use OR equal to, it will just OR the content of this register with this value. So it won't disturb the other column or other bits. That's important aspect. So you have that. So basically the same operation, the clock is enabled 0x14. The same thing that you're doing over here. Where is that? Here. Yeah. So the same thing. The only thing that I'm doing different is I'm not putting that previous zeros here. So this will automatically zero pad because always it takes us 32-bit. So it will make it equivalent to the 32-bit and zero pad in front of it. So this is to enable the clock. This is to make sure the pin port B is 18th, 19th, and first pins are port D's first pins are multiplexed as Gpio. So this is actually 0x100. That is nothing but that 001, right? That is a multiplexing option, and that corresponds to this one here. So interesting way to write it. So PCR 18, port B's PCR 18, 19, and one port D's 1 are actually done. And then direction register port B, so both are combined here. So both are outputs. Port B's 18 and 19 pin are set as output here, and and then setting the output to same. These two pins are made high so that the LED is not glowing. Remember the negative logic. And then port D direction register, port D set output. So the same thing, whatever you used, so many lines of code here, right? So many lines of code. That is actually simplified as this. And now going down, red on, again same here, port B's whatever register. So remember this friend, we are worried about 18, only that guy initially it is 0, right? Both port B's, that guy is 0, and then you are setting the corresponding pin as 1 here, okay? So these two basically, the port B's 19th pin, port D's first pin, both are made high so that the green and blue LEDs are off. Only this one is cleared, that is the red LED is on. That's what happens. And then here red off, all LEDs are made off. That's the thing. Okay, so let's go and debug the same so that you understand it. So let me just give you 1 minute. It will create an error because it has 2 files in, so I have to remove this file. Okay, go ahead and remove the assembly language file. You compile it again. It's good to learn like this, right? Some errors you'll always learn. Go to the debug, connect. Same. Only difference will be, again one more time. Only difference will be it will come to this location. Rest everything is same. Okay, so let me just put F11. You will go here, LED in it, so you can see the clock. Just see the clock. SCG. Similarly, you do all these. It's the same thing. Then you write to here. You nothing is blinking. So the moment I put and I put a very huge delay, so you can see over here. And that's it. So you can go ahead. I'll just go out of debug window. You can go ahead and do this experiment. So this is actually part of your experiment on interrupt and timer. So you'll do this, but I thought instead of doing it, or instead of you really, let me just compile it and download it and see. Doing it all theoretical, it is really boring. So instead of that, it's very, very important to actually understand these concepts earlier. And here, for example, this is a trivia for you. So I downloaded the code, but it is actually not appears to be blinking. So what could be the reason? Just think about it. Answer is very simple and something to think about, right? Okay. So that finishes off this hands-on session. So I have another hands-on session coming up after the lecture, the next lecture, which is basically on the serial communication. So we will discuss about the UART, something in a similar fashion. And we'll see you then. Okay, so hope you're enjoying the lectures. And any questions, doubts, please feel free to use the discussion forum. Okay, thank you.